All right, we're good.
Okay. All right. Welcome, everyone. Thank you for coming to our interdisciplinary seminar. It's a pleasure to have here Dr. Amy Oldenburg from the Physics Department. Astronomy. I didn't realize you have astronomy.
Physics and astronomy.
Okay. And also she's associated with the Biomedical Research Imaging Center at University of North Carolina at Chapel Hill. Dr. Oldenburg got her BS in Applied Physics from Caltech, and she got her MS and PhD in Physics from Urbana-Champaign. And she also worked in the Biophotonics Lab and the Beckman Institute at the University of Illinois. And she's been at Chapel Hill since 2008.
Yep.
And it's a pleasure to have you here. She'll be talking about her optical coherence tomography research work. Thank you. The floor is yours.
Well, thank you, Dr. Krug, and thank you for inviting me to talk to you today. So today I'm going to tell you about my efforts in developing new methods of sensing in biomedical optical coherence imaging. And the methods I've developed for sensing involve the use of both Plasmon-Resonant and magnetic nanoparticles. And here's a little taste of what you'll see in this talk. These are actually some Plasmon-Resonant gold nanorods and some magnetite nanoparticles. And you'll understand what these images mean by the end of this talk. I do have to credit most of these images are actually from the University of Illinois. I just arrived in Chapel Hill in 2008, and I'm still building up my lab, but we are beginning to get our own images here in Chapel Hill in North Carolina. So what is this optical coherence imaging or optical coherence tomography that I'm talking about? Let me put it in the context of other biomedical imaging modalities. So I like to think about the utility of a modality as in terms of its resolution and its penetration depth. How deep into tissue can it provide imaging? Of course, microscopy is extremely high micron scale resolution, but extremely poor penetration depth. It can only see a few cell layers in depth. Ultrasound has an increased penetration depth but decreased resolution. And of course, MRI and CT are whole body imaging techniques, but with millimeter or greater scale resolution typically. OCT, or optical coherence tomography, which I'm going to tell you about today, is a few microns of resolution typically, and provides multiple millimeters of imaging depth. And that imaging depth is actually limited by multiple scattering in the tissue. So it sort of bridges this gap between single cell studies and whole tissue studies. And it's a really exciting place to do research, because now we can study whole tissues but at the mesoscale. And I think it provides a whole new area of biophysics that we can actually do. So what is optical coherence tomography? In essence, it's a form of interferometry that we actually use for imaging. So just as an example, our basic Michelson interferometer is composed of a beam splitter. You put a single wavelength laser incident on this beam splitter. The beam splits into two arms of your interferometer, and a photodetector detects the interference from those two arms. And of course, as you move this mirror back and forth in one of the arms of your interferometer, you get interference fringes. And the period of the fringes is lambda over 2, so if you move this mirror half of a wavelength, then the light path length is actually modified by an entire wavelength, because it has to go forward and back. And so that's why your periodicity is half the wavelength. Of course, this is pretty standard. If we use broadband light, however, so we call this low coherence light, it has many wavelengths at the same time, then what you see at your photodetector is actually what we call a coherence spike. You see interference fringes, but only when the two path lengths between these two mirrors is exactly matched, or when delta L is 0. And if you move your mirror away from delta L equals 0, your interference fringes go away. And this length scale over which the interference occurred is known as the coherence length of the light source. And it's actually inversely proportional to that bandwidth of the light source. And so if you have a broader band light source, you have a shorter coherence length. And why is that important? Well, now I'm going to replace this fixed mirror with a biological tissue. So this is actually an OCT image of a retina, and what happens when we put a tissue in there is that we actually collect backscattered light that comes out of the tissue. So light might travel down here to position 1. Some of it will scatter back into the imaging system. And that light will produce a coherence spike with the moving mirror when the mirror is at position 1. And if you continue to move the mirror to positions 2 and 3, you're essentially probing the backscattering at those depths in the tissue. So this is how we actually build up a coherence image. It's a depth-ranged image of the backscattering in the tissue. And then if we want to build up a 2- or 3-dimensional image, we just scan the laser beam across the surface. So this is the essence of what optical coherence tomography is. Some of the recent OCT systems that you can buy commercially will give you nice 3D images of the finger pad, for example. So in this image, you can see the ridges of your fingerprint at the top. In the middle there, you can see little sweat glands, which allow your sweat to come out into the epidermis. And then that lower layer of tissue is actually the dermis. So it provides, like I said, a few millimeters of imaging depth. And it's also fast. We can look at real-time dynamics. So this is an OCT image of a tadpole at, I think this was at about 10 to 30 frames per second. And as you can see, we can actually see its heart beating in this image. And this is actually quite an old image. There's much faster OCT systems now that can do faster dynamics than this.
What's so special about the African?
So the African tadpoles are actually translucent. So it allows the beam to penetrate very easily down into the heart. So there are a lot of clinical applications of OCT, and since this is a fairly young technology, this is growing quite rapidly. Of course, I showed you that retinal image earlier. OCT is used a lot in ophthalmology. Most ophthalmologists nowadays will have a commercial OCT system to look at your retina. It's also increasingly used in cardiology. For example, you can examine the coronary artery with this catheter probe, so you're actually seeing the sheath of the catheter there. And if you radially scan the beam around the lumen of the artery, you can see into the arterial wall. So it provides imaging of things like atherosclerotic plaques that might cause a serious condition if they are vulnerable, and other things that you might want to see. It's also increasingly used in oncology. Basically, anywhere you could access with a fiber probe, you can do with OCT. So ear, nose, throat, gastroenterology, and so forth. And also, increasingly in dental OCT, you might be able to identify a cavity beneath the surface of your tooth by doing this depth-ranging technique. My particular interest is how to contrast an OCT image. So, for example, if we look at this OCT image of a mammary gland tumor from a rat, what are we really looking at? We know it means there's some refractive index heterogeneity that caused some backscattering, right? So the backscattering is actually a function of these abrupt refractive index gradients. Those occur at surfaces of cells, their nuclei, their mitochondria. Those tend to produce the most scattering. But what does this image really mean? It requires some interpretation. And so my tack is to do some form of molecular imaging, some way to provide diagnostically relevant information to the clinicians. Unfortunately, as we see, the optical response of different tissues are fundamentally not highly contrasted. Now, there are a lot of people working in this area, and it's a very good area, interesting area, but it's a difficult problem. The tissues, you have to really learn what they should look like in order to contrast them. So my tack is to actually use a contrast agent, something that goes into the tissue, and provides an actual physical contrast signal. It might be a nanoparticle or some nanomaterial, and it has some molecule conjugated onto it to make it specific to disease. And the approach I've taken is sort of a synergistic one that requires multiple investigators in multiple areas. I rely on a material scientist to produce novel nanoparticles and materials to probe the tissue, and a biochemist to make it specific to disease. my fundamental interest as an optical physicist is to understand and direct the direction of the synthesis of the nanomaterials so that we can produce the best nanoparticle to contrast OCT images. Because as you'll see, contrasting tissues with a very small nanoparticle is not an easy problem. So what does constitute a good contrast agent in optical coherence tomography? We cannot use fluorescent probes. Everyone in microscopy uses fluorescence because it's very easy. There are a lot of nice molecules out there. But OCT is a coherence imaging technique, so we can't access those fluorescent signals. So we have to think about other ways of contrasting these images. And ways that we might do it are using some kind of particle that has a near-infrared optical signature. We typically image with near-infrared light because tissues have a low absorption in the near-infrared but high scattering. So it tends to be the optical window where OCT is most effective. And so if we use nanoparticles that have a signature such as high scattering, absorption, or very modulated spectrum, then we can sense them against the background. And so in the first part of my talk, I'll tell you a little bit about how I use plasmon-resonant gold nanorods as potential OCT contrast agents. But you'd also like these agents to be modulatable so that you can really discriminate them from the background. And in the second part of my talk, I'll emphasize how I did that using magnetic iron oxide nanoparticles. Of course, you want them to be biocompatible. Both of these materials, gold and iron oxide, are well-known biocompatible materials, truly small in size, less than 200 nanometers, less than 100 nanometers if you can do it, and ultimately getting an antibody or a peptide conjugated to the surface so that's specific to the disease that you want to study. So it's chemically targeted to that disease. So this is a diagram of the apparatus at Illinois that I use, and I have a similar one that I've built here at UNC. And the basis of it is using a titanium sapphire laser, which produces 800 nanometer light with a bandwidth of 120 nanometers. This is really crucial because this bandwidth allows us to get an optical resolution of 3 microns or even less than 3 microns in tissues. The resolution in the transverse direction is determined by our imaging lens. And for these studies, we used a fairly long focal length just for practical reasons, but you can certainly decrease that if you wanted to look at a smaller area. And so this is actually the interferometer. So you may not recognize it, but this fiber coupler is the same thing as a beam splitter. Like in our Michelson interferometer, it splits the beam into 2 arms. One arm is our scanning mirror. The other arm has our tissue. And the light that's collected back from each of these arms is sent into a photodetector. Of course, then we can generate the images. And then some of what I'm going to tell you about with the magnetic nanoparticles involves the use of an electromagnet that's placed above the sample. And now in some of the later images, instead of scanning this mirror, we actually measure the backscattered light using a spectrometer. And we call this spectral domain OCT. And I'll explain why spectral domain OCT is actually preferred a little later in this talk. So let's talk about these gold nanorods. So we thought they might make a really good OCT contrast agent because gold rods are plasmon-resonant. They have a surface excitation of electrons in response to optical wavelengths. And if you have a gold sphere, typically that might be, or it might be resonant just around 550 nanometers. But if you make this, stretch the sphere out into a rod shape, the modes, the plasmon modes, split into a transverse and a longitudinal mode. Now this transverse mode tends to remain around 550 nanometers, but the longitudinal mode now can access these longer wavelengths, 800 nanometers, that we use for the OCT imaging system. And what I'm tuning here, this R, is the aspect ratio of the rod. So we can actually, if we make the rod a longer aspect ratio, we can access longer wavelengths with that longitudinal mode. It also turns out that this resonance can be an absorbing resonance or a scattering resonance. So it still has this extinction peak, But if it's a small nanorod, it will predominantly absorb the light, less than 50 nanometers, for example. Long nanorods, more than 100 nanometers, tend to predominantly scatter the light. And this is an interesting question. What do we really want? Do we want an absorbing nanorod or a scattering nanorod? And the other interesting thing about nanorods is they can heat up their surroundings. So they convert all of this light ultimately into heat. The energy has to go somewhere. And so if you turn up your laser power, you could potentially kill the cells that are adjacent to the nanorods, which you might want to do if your rods are targeting cancer or some kind of disease that would benefit from having the cells killed. Yes?
Is that a unique property of the nanorods or just a function of the size relative to the wavelength?
I would say anything that absorbs is going to convert light into heat. But because these are plasmon-resonant, they're going to do it very efficiently.
I guess my question is whether or not the nanorod absorbs or scatters. Is that a
almost any. It's actually kind of true of any kind of nanoparticle. It's due to this Rayleigh scattering scaling. So what you find even for spherical particles that aren't plasma-resonant, like polystyrene, the absorption cross-section scales with the volume, whereas the scattering cross-section scales with volume squared. So you get a certain critical volume where they're equal, and then above that the scattering dominates. So this comes from underlying Rayleigh theory. So just to give you some motivation, at sort of these near-infrared wavelengths, 770 nanometers, the absorption coefficient for nanorods of a size of 15 by 45 nanometers, which are the ones I'm working with, is extremely high compared to plane spheres of various sizes or polystyrene spheres, which are not plasmon-resonant at all. In fact, you could get plain gold spheres to be somewhat highly scattering compared to the rods, but the absorption for these small rods will still dominate. Now, again, this raises, I mentioned, is it easier to sense absorption or scattering in tissue using OCT? One might think intuitively, well, OCT is sensing backscattering, and you want to sense the particle directly, right? So you want a scattering particle. That might be one's gut instinct. Well, let's look at that in a little more depth. So if we look at the OCT signal as a function of depth in the tissue, we see that if we model the tissue as having some sort of backscattering coefficient that gives us our signal, and the signal is attenuated in depth according to its extinction coefficient, which is the sum of absorption and scattering processes that basically extinguish the light. And so you can see how that works when you look at, for example, a lipid emulsion of varying concentrations. At low concentration, you don't have much attenuation of your signal. At high concentration, it attenuates very rapidly, but the signal at the top is actually higher than it is at low concentration because there is more scattering. So when we put nanorods into tissue, they're going to modify the backscattering and extinction. Those are the two parameters that OCT is sort of can sense. And so if we assume, for example, independent scattering, which might be a broad assumption, we can set this up as a problem where we want to measure the contrast agents, and we want to measure their number density with the highest sensitivity possible. And if we realize that backscattering and extinction are the sum of the tissue, cross-section, and number density plus the contrast agents cross-section and and number density, and same with the extinction, we realize that, hey, if this tissue has a lot of noise in it, say the density of scatterers is highly variable across the image, then these terms are going to dominate these terms. But we can sort of cancel out these large terms by just taking a ratio. We can take the ratio of the backscattering to extinction and sort of define it as a backscattering albedo. Now, albedo is something that astronomers actually use to sense stellar objects, because, such as the moon, for example, because they can measure the amount of light scattered as a function of the total extinction. And usually it's the total scattering compared to the extinction that they look at. Here with OCT, we're just looking at the backscattering, hence the use of the term backscattering albedo. And so all of these ends sort of cancel out. It's insensitive now to end TISH, the density of the tissue, and it only cares about the underlying cross-sections, the backscattering and extinction cross-sections of the tissue. So the nice thing about that is if your nanoparticle has a different backscattering albedo than that of tissue, you can measure that just in those underlying cross-sections being modified. And I sort of modeled this system using Monte Carlo techniques to figure out whether it should work when you put nanoparticles in of a different backscattering albedo from that of tissue. What's the uncertainty in our measurement of the contrast agents in knowing what the concentration of them are? We find that if the contrast agents match that of the tissue exactly, we have a high uncertainty, right? We can't distinguish them from the background. And I did this experimentally. So I put nanoparticles of slightly varied concentrations into lipid. The nanoparticles were of a fixed concentration, but they were added to intralipid, which is sort of a mock tissue that optical tissue imagers use. And I varied the concentration of the intralipid, like we might expect tissue to have a variable scattering intensity. And then I measured the extinction coefficient, and I measured the backscattering albedo. And I had two groups. I had a control interlipid solution, and I had an interlipid solution with nanorods. And if you look along the x-axis, you cannot distinguish these two groups. The control group is not separated from the nanorods group, whereas if we use this backscattering albedo metric, we can separate the groups. We can now sense the nanorods against the tissue background. This is really important because a lot of people were making nanoparticles that were scattering, which means their backscattering albedo was not different from that of the tissue, and they were only looking at the change in the extinction. And I posit that if we use backscattering albedo, we might do a little better. So I also thought, let's add a spectroscopic dimension to this analysis. So let's model the backscattering and extinction as being wavelength dependent. And let's, realizing that, for example, and using a technique called spectroscopic OCT to not just analyze how the overall light is extinguished, but what spectral components of the light are being extinguished. And so, for example, a colleague of mine did what's called spectroscopic OCT in a celery stalk. What he did was he allowed a celery stalk to take up dye in the central tubes of the stalk. Through capillary action, it was actually drawn through. And he imaged that dye actually absorbed half of the laser bandwidth. Actually, the low wavelengths below 800 nanometers were absorbed by this dye, but the long wavelengths were not absorbed. And he found that he could measure the shift in the spectrum of the return light, because of course as the OCT light propagates through the celery stalk, gets backscattered and propagates back, you can sense that the average spectrum of the light has been shifted by that dye. And so we call this spectroscopic OCT, and this is just the control stalk, because now we can sense spectroscopic absorbers in our system. So if we do this with the nanorods, we can do essentially the same thing. We can use them as a spectroscopic absorber by tuning the resonance peak to one side of the laser bandwidth. And we can see that as we put in intralipid increasing concentrations of nanorods, that we can start to sense a spectral shift. So in this case, I was measuring the spectrum of the extinguished light. I was modeling what the extinction, the wavelength-dependent extinction was of the tissue. Well, actually, these are experiments, and then I was measuring that. So does this work in real tissues? It seemed to work really well in the phantoms. So I got some breast tumor biopsy specimens through Carl Foundation Hospital. And we looked at the spectroscopic OCT signal from serial slices in the tumor. And then I injected nanorods into the surface. And then I took another set of serial slices. And I saw that after injecting the nanorods, that, yeah, there are some sort of hot spots here, red spots that might correspond to nanorods absorbing the light. But there's a lot of background spectral modulation here in the a priori images. So it's not really obvious that this is actually going to work yet in real tissues. So what is the outlook? Well, we know that it turns out that these absorbing nanorods are actually easier to sense against a scattering tissue background because they can modify the backscattering albedo. So I learned that, and I learned that we can get high sensitivity in tissue phantoms, and even if we don't know the concentration of the tissue phantom, we can get high sensitivity. But there's still a lot of background noise that we experience in real tissues. So we have to do something more if we're really going to use this for imaging purposes. So for the nanorods, I think one of the future techniques we might use is looking at orientation contrast. So you know that nanorods will exhibit rotational dynamics that are determined by the viscosity of the medium. If it's a more viscous medium, the nanorod's Brownian motion will be much reduced. And we might be able to actually use what's called polarization-sensitive OCT to sense that, because it turns out that these nanorods have 1,000 times greater cross-section when the polarization is parallel to the rod. So in this sense, they're a really strong orientation sensor in tissue. And this has actually been shown in microscopy, but has not yet been used in tomography. And it might actually be a really good way of doing tomographic imaging of local viscosity. So that's one direction that I think nanorods might be very useful. So now let me move on to the magnetic nanoparticles. So I sort of showed you rods and how I thought about contrasting them in tissue, but we had trouble because the tissue had a lot of background in that spectrum, background modulation. Well, it turns out human tissues are not magnetic at all. They have a very small amount of diamagnetism. The magnetic susceptibility of tissue is on the order of 10 to the minus 5. It's typically dominated by that of water. If we compare that to a superparamagnetic nanoparticle, say of magnetite or some other magnetic iron oxide, that magnetic susceptibility is on the order of 1. So now we have a potential contrast of up to 10 to the 5th that we can use as a handle to do contrast imaging. And this is just a TEM image of some of the nanoparticles I was using. They're from a company called Ocean Nanotech, and they very nicely conjugate them so that they're dispersed in water and salines that you might use for wet tissues. So how are we going to use these particles? Well, we can put an electromagnet above our sample while we're imaging with the OCT system. And if we apply a magnetic field, and more importantly a magnetic field gradient, we can actually pull on the nanoparticles with an induced magnetic gradient force. This is basic electromagnetics. The force is proportional to the particle volume, the magnetization of the particle, and the gradient of the magnetic field. And the particle magnetization we measured with squid magnetometry. It just, as with most superparamagnetic particles, it has a very high susceptibility, so it goes up very rapidly, and at just about 1/10 of a Tesla, it started to saturate. The thing is, once it saturates, this force only scales linearly with the field, whereas before it saturates, this force scales as grad b squared, actually. This is important, and I'll explain in a little bit. So how are we going to use this for imaging? So we can pull on the particle. The particle is dark. Magnetite, maghemite are both dark crystal structures of iron oxide. They're not going to give us an optical signal. They're not plasmon-resonant, so their absorption is insignificant either. But it's going to deform adjacent tissues that it's mechanically coupled with. So if the particles are embedded in a solid medium and you pull on them with this magnetic gradient force, they're going to deform the tissue. That tissue deformation directly corresponds to a shift in the interferogram that we get when we do OCT. And in fact, we can look at phase shifts in our interferogram. They're directly proportional to that position shift of the tissue. And in fact, because this phase is so highly modulated at half the wavelength, we can sense, turns out we can sense displacements on the order of only 10 nanometers. So now we have a very sensitive position measurement that we can take using OCT. And so this actually works beautifully. So here's an image of an excised rat mammary tumor. And in the left, this is just the red is just showing the basic OCT image of that tumor. And on the right, I've injected magnetic nanoparticles, and they've sort of diffused inside the tumor. And you can see the locations of them displayed in green. And I created this image. I'll show you a little more about the image processing to create these images. But basically, it's by modulating the magnetic field and picking up those modulations at that specific frequency. This works with cells, so you can load cells. These are called macrophage cells. They happily take up any foreign particles in their vicinity. They're basically the garbage dumps of the human body. And so we loaded some cells with magnetite particles compared to control cells. OCT is a 3D imaging modality, so we dispersed the cells into a gel matrix. And we did some OCT images of that gel. And I'm sorry that it's not showing up all that well, but in red, this is the OCT image. You could see some locations of high scattering corresponding to positions of cells. And now if we look at our magnetic signal layer, we can see that very specifically now, specific locations of magnetically labeled cells can be tracked in this three-dimensional tissue construct. So we can track cells, we can track the particles. One problem is that if things are moving, like this tadpole heart, that motion can confound the motion from the magnetic particles, right? I mean, because both things are moving. And so we have to make sure that our OCT sampling time is actually short enough so that it's shorter than the correlation time in the tissue. So there's something called the speckle correlation time. So coherence images have something called speckle in them. And when tissue has Brownian motion or cardiac motion or respiratory motion, that speckle moves. And there's sort of a characteristic correlation time over which the speckle from one frame is no longer correlated with that from the other frame. And so if your sampling time is much greater than that speckle correlation time, we can't do magnetomotive OCT because we lose all of that displacement information. So basically, we have to sample rapidly enough. And in fact, if we sample very rapidly, we can get shot noise limited imaging. And it also determines our available dynamic range. So how did this work in vivo? So I actually, again, I looked at this tadpole with a beating heart in real time. And I did magnetomotive OCT of a controlled tadpole. So this is imaging from the top, imaging from the bottom. And its heart was beating here and it had some background, as you see. And then I had a tadpole that I placed in a tank with magnetic particles. And it basically fed the particles through its filtering system. It has suction feeders that filter out the particles in the water. And it turns out those particles ended up very well localized to its intestinal tract or its gut, which we see a very strong signal here corresponding to where those particles are. It was also excreting the particles while we were imaging, so it got embedded in the molding clay. But suffice it to say, we got a very strong magnetic signal from those particles. But what about that heart? So here I'm going to show you, this is the image of the heart, and then this is the image of the intestine that actually had particles in it. And I was showing you these images on a scale from 0 to 18 dB. But if we actually use a symmetric scale, looking at the imaging signal from -18 to 18 dB, we can see that in the heart there are these positive and negative lobes. So what that means is sometimes the heart's beating was correlated with the magnetic field modulation, and sometimes it was anti-correlated. And that's because the heart's beating really wasn't correlated at all. It just sometimes happened to line up and sometimes happened to exactly be opposite. And if we were to average this image over a larger volume, we could easily see that this heart is a non-magnetic structure. It would just have required more volume averaging. Whereas if we look at this intestine, it's entirely a positive lobe, entirely correlated motion, and so we can definitely say that this is a magnetic structure. So I want to get to, I mentioned earlier that we actually use a spectral interferometer in some of the later experiments to measure, take the OCT images. The reason for that is we don't have to mechanically scan that delay arm, and it allows us to get better phase sensitivity to these small displacements. If we have to mechanically scan the arm, we get very large phase noise. And also the mechanical scanning takes time because it has inertia, and it limits the speed that we can scan with. There's also a signal-to-noise ratio advantage to spectral interferometry because we can detect all of the pixels in depth at the same time. And I'll show you why in just a little bit. So when we do time domain OCT and we scan that reference arm, we're measuring the mixing, the interference between the sample electric field and the reference electric field, right? And we get a signal as a function of tau, which is that mirror depth, the mirror delay. And so usually we process this signal by taking a Hilbert transform of this time domain signal to get the complex analytic form of the signal. So you might have a sine function, and then when you take the complex analytic part of that, you see that it's just a modulated phase function. So it's like cosine plus I sine. And this turns it into a convenient form for phase analysis. Now, if we do spectral domain OCT, we actually measure the interference in spectrum between the electric field from the sample and the reference. We don't have to move this delay arm anymore because if we take this spectral signal that we get, the intensity off the camera, off the spectrometer, we take the Fourier transform of it, we actually get the same complex analytic signal that we get when we do time domain OCT. And the reason, this is actually described by the Wiener-Khinchin theorem. It's something that astronomers also use. So we can now use this spectral domain signal, and we can look at this phase and how it's modulated by our changing depth, by our tissue deforming in time, delta z. So this has actually allowed me to speed up the imaging quite a bit. It's allowed me to sample more rapidly. I actually generated a technique where if we modulate the magnetic field at a frequency that's faster than the time it takes to scan across one resolution in position, we can actually take a magnetic image and a regular OCT image in one scan. And what happens is when you take your OCT image, you now have your structural OCT data at the low frequencies. So you're scanning across, you might get, whoop, oh, here's a scatterer, and it's a very slowly changing function as a function of the scan position. And then here is your magnetic signal, which is modulated at a higher frequency. And now you can simply bandpass filter your signal to generate your structural OCT image and your magnetic OCT image from the same set of data. So this worked really well. In fact, it worked so well that I started to see diamagnetic motions from the tissue itself. Why would I get motion from the tissue without nanoparticles? Well, tissue is diamagnetic. And so if you think about it, when we apply a magnetic field gradient to these particles in the tissue, the particle, of course, is pulled towards the coil. But the tissue, because it's diamagnetic, it's repelled from the coil at the same time. And there's actually a force balance between these two. That force balance depends on the relative volume percentages of each of these things. And so if we have, say, we have a volume loading or volume fraction of the particles that's greater than some critical volume, then this net force balance is actually towards the magnet. But if our volume loading of particles is too low, then the next net force balance is actually away from the electromagnet. So I call this a critical field because above it, or critical loading of particles, because above it we actually get this net paramagnetic motion. And it's related to the magnetizations of the tissue compared to that of the particle. So what happens is if we look at this critical concentration, if we increase the magnetic field, it actually requires a higher volume loading of particles to get this net paramagnetic motion. And that's because your diamagnetic magnetization keeps going south while your particles have saturated at about 1/10 of a Gauss. But of course you want to have enough magnetic field that you're above noise, which is this blue line here. So if we kind of combine these two effects, we find that there's an optimum magnetic field strength that you can do OCT imaging at, and that's about 1/10 of a Tesla. So really I found that the coils that I was using, providing about 1/10 of a Tesla, are already optimal, and I don't need bigger magnetic fields. And then I realized not only that, but we can reject this diamagnetic background that I was getting, because now we can look at whether the motion is towards the magnet or away from the magnet. And you can look at the phase lag of these motions and create a filter to filter those out. And so in essence, what I did here, and I'm going to move along pretty quickly, I found that if I filter out the diamagnetic response, that my dose-dependent response was much improved, that's this top line here, compared to not filtering out the diamagnetic response. And that's just an image of particles diffusing into rat tissues as a function of time. So I use this system now, it's very sensitive, to actually image the diffusion of magnetic nanoparticles that are applied to the top of a tissue and show that they do indeed diffuse in over time. And another interesting aspect of these particles is they're very similar to what they already use for contrast in magnetic resonance imaging, and we proved that. We did some spin echo MR imaging of the particles. Here they're at varying concentrations ramped from 0 up to 30 parts per million, and so you can see that they have this negative T2 contrast, which is arising from the paramagnetism from the particles. And as another neat application, I can't take credit for this slide. This was actually done by an MD PhD student at Illinois. He actually encapsulated a ferrofluid of magnetic iron oxides in a protein microsphere. And then he labeled that protein microsphere surface with an RGD tripeptide. So it's a specific peptide that recognizes receptors that are overexpressed in atherosclerosis. And when he washed coronary arteries from rats that had atherosclerosis with these particles, he found that they stuck to the lesions inside the artery. And he found, using OCT, using magnetomotive OCT, that he could contrast this lesion. And here's the histology that shows that lesion at the same time. So I'm going to shift gears now for the last 10 minutes, I think I might have 10 more minutes, to other things we can do with these magnetic nanoparticles. We can actually now probe the elasticity of the tissue. Now, elastography imaging is really important in biomedical imaging. It's sort of up and coming. Techniques such as magnetic resonance elastography, ultrasound, various techniques with ultrasound, because tissues tend to have, pathological tissues tend to be stiffer in general, or they tend to have a different stiffness anyway. And so this is a functional metric that we can actually use to contrast disease. This is because different cell types are present in disease, or they might have a different extracellular matrix, or there might be more vasculature, and more vasculature tends to, more blood vessels tends to make the system stiffer, such as tumors, which have their own blood supply. So if we can do imaging of the elastic properties and correlate these viscoelastic properties with disease, now we can contrast disease. So we can do this with magnetomotive OCT, and in the interest of time, I'll kind of skip through this. The basic idea, why would we want to do this with my system, is because now we have interferometric strain detection, so it's very, very sensitive. It's high bandwidth, it's high speed, and not only are we sensing it, but we might even be able to, we can image the strain in a 3D volume. And we can use these magnetic nanoparticles diffused into tissues. They have negligible inertia, so you don't have to worry about the mechanical coupling of a cantilever system or how that modifies the stiffness of the tissue. And they can apply a distributed body force to the tissue. So in So the basic idea, previous colleagues of mine did this with a mechanical wave driver. They didn't use particles. And they found that if you mechanically actuate tissue, and actually this dotted line, I should say, is the applied stress as a function of time, then you can measure the resultant strain. And so this is actually the OCT image drawn here. And then this is sort of the extracted signal that we get from that OCT image. So it's sort of imaging in one spot, and we're watching a scatterer move up and down in time. And we can see that this is phase lagged with respect to the applied stress. So we can actually write this as an elastic susceptibility. Stress over strain is elasticity, and these are actually can be written as complex numbers because they have a phase. So it's an elastic modulus with some kind of phase lag. Why is this interesting? Well, it turns out if I do this with magnetomotive OCT and I sweep my frequencies, I can actually measure changes in the strain as a function of frequency. So what I found here is tracking the displacement as a function of time. And we can see that, and on the top here I'm showing the actual frequency that I'm driving it with. So when we hit like a frequency of 100 hertz, you see that we got a resonance peak here and other peaks here. And so this chirped excitation actually allows us, and I'm going to skip over the data processing, it allows us to extract the mechanical frequency spectrum of the system, or the mechanical spectrum. And so if we convert this displacement into the complex mechanical spectral response by basically dividing out the driving chirped force that we're using. This is basically standard processing that you might use for a linear time invariant system. Then you find that you get these resonant peaks at specific frequencies, and you get your mechanical phase lag. So this is the argument of that spectrum. It's actually flipped from 0 to pi at each of these resonances. And guess what? That is exactly the solution for a linear damped harmonic oscillator, which is well-known Lorentzian function. And in fact, we can take this data and fit it to Lorentzian, which has a natural frequency at the center, and it has a viscous damping term that determines the width. And in fact, it fits not just the amplitude of that function, but the phase of that function. So we find that this phase does flip from 0 to pi. It actually makes sense. And the images I just showed you, those are in an agarose gel. They also actually work in real tissues. So we had a rat liver and a rat kidney, and we did this analysis to it. We allowed the particles to diffuse in. We measured the mechanical frequency spectrum, and we got the same sorts of Lorentzian-looking curves. So can we actually use this to predict the elastic modulus? The answer is yes, if we know the boundary conditions. In this case, I did a study where I used agarose cylinders of a known length and radius. Of course, it turns out what we're measuring are longitudinal modes in the cylinder as we push down on the particles axially. And I got it to fit the model very well. I found that gels that had a consistent elastic modulus, if I varied the height of the cylinder and I measured all the resonance modes, I found that it was very consistent with this longitudinal mode solution. I also found that we can then extract the elastic modulus of the medium by looking at these modes. So we can fit the mode structure to a prediction of the elastic modulus. I found that when I ramped the agarose concentration, I was able to fit agarose concentrations over 2.5 decades. So from single kilopascals up to almost megapascals. And I found that if we fit this to a phenomenological model with alpha and beta, that my values for alpha and beta were almost too good, almost too well matched with previous measurements of agarose. And then can we actually do this again? We did another study in real tissues. I tracked elasticity changes in a liver while adding formaldehyde. So if you put formaldehyde on anything, it cross-links all the proteins and it makes it stiffer. And so we monitored the stiffening in the liver over time. You can see at 0 minutes, its resonance frequency is at 50 hertz, and then its resonance frequency shifts up at 29 minutes, and then at 67 minutes, it shifts up again, and then it becomes so stiff that we really don't get much strain response from it anymore. This allowed us to sort of qualitatively follow the increase in the modulus. Now I should say that because we didn't know the boundary conditions of that liver, we can't directly extract the modulus. We can only say what its relative change was. So I just quickly threw the slide together. I wanted to mention there's a neat application for this, and that is studying the damage mechanisms to the human bronchus in patients who have cystic fibrosis. So we've actually been doing a pilot study with the Cystic Fibrosis Center at UNC, where if we can do some OCT images of the bronchial wall, and you can see that this is actually a CF lung bronchial lumen, and it's very corrugated in appearance. And this is actually a normal human lung. And so you can see the difference here. The CF lung is obviously structurally very different. What we're really interested in is we have this model system for the bronchial walls. And what happens in cystic fibrosis is you get chronically infected and those walls break down due to the chronic infection. And we want to understand the mechanisms of the breakdown of that matrix. And so this model system will allow us to do that because we can culture lung epithelial cells on a scaffold. We can study how they modify their scaffold in response to anaerobes that are added to the system. And elastography, OCE, this technique will allow us to monitor elasticity changes in the scaffold somewhat non-invasively. So we can track it over time without having to stick a cantilever in and actually query the system. And I apologize, this is just an OCT image of them. We actually do have elasticity data of these scaffolds, but I didn't have a chance to get it up there. So just to summarize, I told you a little bit about plasmon-resonant gold nanorods and how they provide absorption and spectroscopic contrast, but maybe not quite well enough to do real tissue imaging yet. I hope I've sold you on the wonderful uses of magnetic nanoparticles, how they really give us good contrast imaging, and also have this potential multimodal application with magnetic resonance imaging. And then elastography is really exciting because now we can measure these functional tissue properties. Quantitative modulus if we know the boundaries, and a relative modulus for unknown boundaries that we can sort of track over time. So in the future, I actually want to look at hybrid magnetic plasmonic nanoparticles, which might have even better contrast than the particles I've shown so far. And that would be in collaboration with, again, materials and nanoscientists, nanochemists. Again, looking at viscometry by looking at the rotational dynamics of tumbling nanorods, advancing this elastography and actually using finite element models to understand what the elasticity is of an irregularly shaped tissue, and then trying to advance this into an elastography imaging techniques by using inverse models of how the elastic waves are scattering in the tissues. This is, of course, extremely challenging, but it's a future long-term goal of mine. So I'd like to acknowledge both the group that I came from at Illinois, and of course, I'm now at the University of North Carolina at Chapel Hill. Thank you very much.
Any question?
How exactly do you define contrast? Is it that the targets that you're looking at in the tissue have similar backscatter profiles as everything around it, or that you just can't see the thing that you want to image because there's all this stuff in front of it?
So in the most general sense, contrast is the signal, whether that signal is the optical signal or maybe the magnetomotive signal, compared to the signal that you get in the absence of the nanoparticles. So, because you always get some background noise, either in your optical signal or your magnetomotive signal.
So really it's the contrast of the particles, not necessarily of the image.
Not of the final disease, which again requires some link with like either a chemical linker, like a peptide or an antibody to target it to disease, which I think of as the chemical sensitivity contrast, or with the elastography, if that's also associated with disease, then that's another layer that you have to put onto that to actually say you're detecting disease. All I'm saying is I can detect the particles.
Right. So if the particles have good contrast relative to the tissue background,
Right.
if you can attach these things to specific targets, that's the goal.
Right. Yes. So that's a non-trivial step.
Right.
But yeah.
What about the other way around? So not attaching the particles to specific targets, but attaching them to the background. Does that help you any?
That might work in elastography if we wanted to just measure elastic properties and then understand something about the tissue from those measurements. But I'm not really sure, otherwise what merits it might have. You might use, unless you're using them for therapy as well. You could put particles in and use them as a hyperthermic therapeutic. Yes.
Thank you for the presentation. I have to say I was fascinated by really all the topics, but especially the first part, because ultimately nanoparticles and polarization are very much things that I enjoy studying and thinking about. And so I have two questions related to the polarization impacts, although I acknowledge you did say it was kind of mostly future.
And I thought about it more than I've presented here,
Sure,
so go
well,
ahead.
Then two questions. The first one is, as I understand polarization OCT, the classic way is a signal that's coming in response to the different birefringence and orientation properties of the different tissues.
Right.
So it would seem that that should complicate the possibility of using the very strong dichroism of the actual nanoparticles. And how would you handle that is really just the broad discussion. I was wondering if you could respond.
So there's two, that's a very good point. There's a native birefringence in the tissue and there's an optic axis, and you can measure both of those things, and it's shown that collagen has a high birefringence. But the gold nanorods, as they're tumbling, they're going to blink on and off. They're going to have a dynamic polarization sensitive signal. And I posit that the time evolution of that signal is going to look completely different than that of the native tissue. So it's going to show up as there's this characteristic blinking at this frequency, corresponding to sort of the Brownian motion, and it's going to be it's going to have a higher variance at that frequency than native tissue would. That's just sort of a static birefringence. The other way is, and actually I didn't present that here because it's sort of it's a project in process, but is actually coupling it with a ferromagnetic domain so that we can actually twist them. And now we can exactly control, we know their orientation, and we know we can now modulate the response.
Yeah, that's fascinating. Certainly, my interest and background is more in liquid crystals, in both, especially electric field controlled liquid crystals, but also magnetic field. So that sounds like indeed a great idea. My second original question was related to this tumbling and this. You called it viscometry?
Viscometry, maybe I should call it rheology, I'm not sure.
That's fine. I'm surprised that you would expect to get a signal from, as you said, tumbling of individual nanoparticles. It would seem, I'm just surprised. Are you sure?
Well, they've done it in microscopy. So they've shown if we focus down on a single nanoparticle, we can look at its orientational dynamics, and it's related. Yes, we're going to have, in OCT, we're likely going to have an ensemble of these things in the beam. So it's going to be an average ensemble, and I hope that, I'm not sure, but I hope it falls out of the temporal dynamics. That again, the other trick is we'll look at anti-correlations between orthogonal polarizations. So if you see a hot spot in, horizontal polarization and a corresponding low spot in vertical, then hey, that's probably because it turned out of vertical and went into horizontal. So maybe playing some tricks like that.
Yeah.
But
well, good luck.
Thanks. It might be overly optimistic.
So it's still fascinating. It's worth looking into.
Any other question? I do have a question. You mentioned that at some point that you could, in fact, I have actually two questions. The first one had to do with the lack of diffusity, or diffusion, if you will.
I wouldn't say there's a lack.
But couldn't you use that, or rather also as a measure of characterization? And if you can quantitate it.
Quantitating diffusion particles.
Or lack thereof.
Or lack thereof. Yeah, well, there's some research in that. I don't immediately know what that tells us about. Maybe it'll tell us something about the tissue and its structure.
That sort of dovetails into my second question. Second question is, what are you envisioning this, for instance, being used perhaps at sort of a distance? Could one envision using this at a distance, almost like in remote sensing type of?
I don't see why not. Well, in terms of the magnetic actuation, or the magnetic
Yeah, in other
motor?
words, suppose, I mean, granted, you're working with particles here, but
Right.
my particles are human beings.
Okay.
Okay, so they're much bigger,
Uh-huh.
much more complicated too. But anyway, but imagine that we were to probe an environment, of such scale, and
There's certainly a lot. I guess I kind of think the general category of what I'm doing is sort of like standard deviation imaging. You're looking at temporal dynamics and you're, extracting differences, contrasting based on those. So I guess if there's some contrast in the, temporal dynamics of your human beings, that, some are moving fast, some are moving slow. But I'm not really sure yet.
yeah, I guess I was thinking more, for instance, of your nanoparticle.
Okay.
How you could use basically the resonant modes of your
Okay.
of your
Well-
nanoparticles as the basis of your.
Well, one thing I was thinking of doing, and it wouldn't necessarily be with OCT, but it would be interferometrically detecting surfaces and looking at mechanical modes on those surfaces. So you could now maybe watch the elastic wave propagation.
Yes.
And one thing I was thinking is if you could do this over enough of the tissue, you could now use inversion algorithms like seismologists use. They measure surface waves on the Earth, right? And they extract the full elastic properties of the Earth.
In a differential mode.
Mhm.
Yes.
So, and yeah, there's no reason you couldn't do that interferometrically or, with some sort of shearing interferometer to track tissue displacements. So yeah, I don't know that you would need magnetic particles to do that. So you might just actuate
Yeah.
them.
All right. If there are no more questions, let's thank our speaker again. Yeah.
Oh, just one more question. Would an absorbent dye do the same thing as particles would? If you could somehow inject a dye to change the backscattering albedo?
It would, yeah, that would work for backscattering albedo, yes. I think the things that the rods bring to the table are the potential for photothermal therapy at the same time. But in theory, the dyes, there aren't a lot of dyes that are FDA approved. There might be one called ICG. And in some sense, then you have to target more of the molecules to a single cell because a single dye molecule doesn't have nearly as much contrast as a single nanoparticle. So there are some pros and cons,
You mentioned hybrid particles for your next step. What would be your sort of ideal hybrid particle? Would it be like a iron oxide nano spindle or something coated in gold, or?
Yeah, it would probably be a nanorod because it's resonant at 800, in the bandwidth of my system, overcoated on a ferromagnetic core. So something that we can twist. The core, I don't care about the shape as long as when I apply a field, I know the direction of the rod that results.
All right. Let's thank our speaker again.
Yeah.
Yeah, no, that's what Peter was. Yeah, he's trying to do the